And we are on the last part. We are on unit this part, periodicity. Periodicity, I already started. If you remember, in the extra review class, we discussed the atomic size, effective nuclear charge, size of the ions. So here is a question. And we discuss isoelectronic species also. So N3 minus and N, which one is going to be bigger in size? Mhm. Which one is bigger in size and why? Everything is written here. Yes, Afan, which one is bigger in size? Mhm. Yes, N3 minus is bigger in size. Why? Why is not written here? So can you explain why? Use only one word. Yes, this is bigger because, Azuni, can you tell me? Sanjana? No, Anzara. Nuclear charge in the nitrogen is +7. In this nitrogen is +7. So do you think nuclear charge is different? They are the same element. Atomic number is 7. Atomic number is 7. So please watch the recorded session. Make proper notes. Read my notes. Okay, you have to work hard, children. Both of them have this +7 nuclear charge. Yes. N3 minus has 10 electrons on +7. N has only 7 electrons. So in which case the effective nuclear charge is more here. The effective nuclear charge, not the nuclear charge, Ansara. The effective nuclear charge. Effective. Its charge is more. And here the effective nuclear charge is less. Yes, Sanjana. Good. Okay, so that's about your these things. So these are important, very, very important. And I cannot keep repeating. You have to go through the videos if you are not able to understand. Do the question. Doing the question is the best way of memorizing, which I see that you people are not very regular in that. Okay, the next topic is ionization energy. So if this is the nucleus and this is the atom and here is the electron, you know that electron is attracted to the nucleus. And if this is the atom, this is the nucleus, and here is the electron. In which case, removal of electron, I want to remove the electron. I want to take out this electron. In which case, removal of electron is easy in atom A, in atom B. In which case? In smaller one or bigger one? Is easy in this case, yes. So now ionization energy is the energy needed. It's endothermic. It's energy needed. I have to add energy to remove the electron. And the energy which is needed is called as ionization energy. And removal of electron is easy here because the attraction is less. So one factor which is going to control the ionization energy is atomic size. So what happens to atomic size across the period and down the group? Yes. So what happens to atomic size across the period? Atomic size across the period? Yes. Across the period atomic size. Are you writing atomic size or ionization energy? Azuni is right. Across the period, atomic size decreases. See, this is across the period decreasing. Okay, okay, this is isoelectronic species. It's a different thing. But across the period, we know that atomic size decreases, right? And ionization energy will size across the period decreases. Ionization energy across the period increase. What happens to atomic size down the group? Atomic size down the group, what happens? Atomic size down the group increases. Across the period decreases, down the group increases. If down the group atomic size is increasing, what happens to ionization energy? This is size. Size is increasing. Ionization energy will decrease. This is one factor, atomic size. And you know the reason? Okay, now the next thing, memorize it right away. Atomic size across the period decreases because effective nuclear charge is increasing, number of shells are not increasing. But down the group, atomic size will be increasing because shielding effect is increasing. There are more shells. More shell means more bigger size. If you check my notes, these pictures are from my notes. So children, please, everything is available on the website. I cannot provide you everything here. So check my notes and start memorizing. Finish this particular topic this weekend. Unit 1. Now start with Unit 1. And this coming Saturday, I'm going to discuss 2017 full length paper. I want you to come prepared, go through the paper, try to do it yourself. Okay, and then see the difference when I'm going to discuss with you. You will understand better. If we can practice 4 or 5 papers like this, so that will be really good. Okay, Aditi, no problem. Okay, so now this is one factor. So we are working with ionization energy. So can all of you answer my question? Across the period, left to right, what happens to atomic size? Period, left to right. What happens to atomic size? What happens to ionization energy? Yes, Ritika, very good. Group, what happens to atomic size? What happens to ionization energy? It increases. Is it difficult to memorize, children? Okay, and if you read my notes, every reason is there, and I discuss the reason. Those who have joined late, I already discussed the reason for the ionization energy. Factor 1. Second factor is electron configuration. Stability of electron configuration. It's written here. It's factor 2. It's there in the notes also. Stability of electron configuration. Which electron configurations are stable? Which electron configurations are stable? Fully filled and exactly half filled and noble gases. So if you see fully filled shell, fully filled, like noble gases, NH2, NP6, extras. This is the general configuration of noble gases. This is extra stable inert configuration. First thing. Second, again fully filled, but not an inert configuration like NS2. So which family has NS2? Which family has NS2? Can you identify the family? with 2 valence electrons. Which family is this? 2 valence electron, children. Group number tells you the valence electrons. Yes, group 2. Very good, Afan. This is group 2. Perfect, Afan. I'm very happy that you are working really nice now. Okay, so NS2, group 2. Children, is it okay with all of you? So please practice general configuration of S block and P block. And exactly half filled. In exactly half filled, you are not going to consider S. Exactly half filled, we are going to consider only P and D. But D is not the part of our learning, so leave it. So it is, this one is exactly half filled. NS2, NP3. Which family is this? Can you tell me the name of the family? Which family is this? NP3. You know, P can have maximum 6 electrons, but it is 3. If you look at the box representation, it's like this. In my notes, everything is there. Though their number of pages are more, but most of them are pictures, just to make you understand. So when you start reading the notes, it's not going to take much time. Underline that this I have to memorize, start memorizing. Open the notes and start memorizing because you have heard these things many times from me. So you will understand. Now I will say memorize, memorize, not understanding. Okay, don't worry, memorize because exam is very close by. So these are the three which are going to be with extra special stable configuration. So stable configuration means easy to remove electron or difficult to remove electron. If I have this particular element with 2 electrons here, this is NS2 configuration. Is it easy to remove electron or difficult? Difficult, very good. If it is difficult to remove, then ionization energy will be high or low? Ionization energy will be high. So whenever you see these configurations, they have exceptionally high ionization energies. Out of these three conditions, which one has the maximum ionization energy? One, two, three. Which one has maximum ionization energy? Highest. One, very good. Can you give me the reason? They are noble gases. They have, use all these terms. They have a full octet. Octet rule, magic number 8. They have full octet. Right? That's why. 8 valence electrons. Yes, it's a noble gas with 8 valence electrons. 8 is the magic number. Elements, they all want to have 8 in the outermost shell. But yes, then we did expanded octet also later on. So are we okay with this second factor? Second factor, we are okay. Now we are going to apply it. Let's apply. So I'm erasing it because I'm going to move on the periodic table. You can see here, periodic table. Okay. So what's the general configuration of family 1? Family 1. Now, alkali metals. What's the configuration? So I'm giving you practice on general configuration. General configuration is of the valence shell. What is the valence shell of this? 1s1. This valence shell 2s1 like this. So what's the general configuration? ns1. Do not count this configuration as exactly half filled because it's only one orbital with 1 electron, so there is no stability factor. So just leave it. What's the general configuration of this family? This is 2s1, 2s2. This is 3s2, 4s2. So general configuration is ns2. Memorize it. Leave this part. What's the general configuration of boron family? Boron family. Just write the configuration of boron and pick up the outermost shell, and in place of number put N. No, no, no. Outermost shell. Aditi is not NP1. No. Outermost, complete outermost shell. No, Anzara. Complete outermost shell is NS2 NP1. Write the configuration of boron. Is 1s2, 2s2, 2p1. What's the outermost shell? This one. So don't say NP1. You're understanding this, Anzara? You have seen your error? Aditi, Afan? Now, what is the outermost shell of this helium? Check the period number. Practice, children, practice. Period number 6. So, what's the outermost shell of thallium? Yes. Who is this? Aditi. Very good. Thallium is 6s2, 6p1. That's the outermost shell. I know that there are F and D, but outermost shell by definition is the one with the highest N value. Okay. So what's the general configuration? Only few children are answering, like Afan is answering, and Zara, Aditi. What about rest, Sanjana? Ritika? Arya, you're there? Okay, Sanvi. Sanvi, last time I kept calling your name, but you didn't respond. Aslisha, Ashwin, Ariba, start answering. This one is general configuration of carbon is general configuration of carbon. Sanvi, try to answer. You have understood how we are writing. We have done it earlier also. Okay, general means I think you are giving me a carbon. Yes, Afan. General is NS2, NP2. Very good. What's the general configuration of nitrogen? NS2, NP3. Okay, now oxygen, NS2, NP4. Fluorine, NS2, NP5. And noble gases? Noble gases, all of you, please give the general configuration of noble gases. NS2, NP6, yes. And this is extra, the most stable. Now answer my question. As I'm moving down the group, like this, down the group, is there any change in the stability of the configuration? As I'm going from lithium to rubidium, is there any change in the stability of configuration? Because you remember I told you which configurations are stable. NS2 is stable, this NS2 NP3 is stable, and these three are stable. No. So this factor, stability of electron configuration, is not valid down the group because every group has same configuration. Elements of the same family, Sanvi, they have the same configuration. Am I right, Sanvi? Start interacting here, Sanvi. Elements of the same family have same general configuration. So stability of the configuration is not valid down the group. So down the group, you focus only on atomic size. You will not face any problem. Just go for atomic size. And what happens to atomic size down the group, children? What happens to atomic size down the group? It increases. As atomic size increases, what happens to ionization energy down the group? Ionization energy decreases. Memorize it right away. Okay, now let's move across the period. So is the stability of configuration changing across the period, children? Let's pick up a period. I'm picking up this period, period number 3. Is the stability changing? Yes. Okay, so what happens to ionization? So let's discuss ionization energy across the period and let's make a graph. I'm doing a very good question here, Ashwin. I hope you're there because you're not answering anything. Ashwin, you're there? Ariba, Ashwin, check here. Here is the ionization energy and here is the atomic number. We are talking about period number 3. So according to size, what happens to size across the period? What happens to size? Decreases. What happens to ionization energy? Increases. I should get a graph like this. Am I right? See ionization energy and atomic number. So here is my sodium. This sodium. And here is my magnesium. Am I right? But where is my aluminum then? It should be here. But no, it's down. It's here. Aluminum is here. Why? Because magnesium has extra stable configuration. You remember NS2 is more stable. Energy needed to remove electron from magnesium is higher than aluminum. So there is a drop. You can see there is a drop. The line is not going straight. This is exceptional behavior arising because magnesium is more stable than aluminum configuration. Aluminum is NS2, NP1. Just by removing one electron, it will become stable. So it's happy to give away one electron. Aluminum is happy to give away. Yeah, definitely. Sodium is bigger in size also, Aditi. Remember, I said the trend should go like this. This is a regular trend based on size, based on this factor. This yellow is the regular trend. But then we have stable configuration, stable electron configuration. Here is aluminum, right? Which is less stable than magnesium. So aluminum is lesser than. So can I say third period elements? These are the third period elements. Sorry, not period, third group. Third group elements, ionization energies will be lesser than second group elements. Is it okay? Ashwin, you people are getting this? And what is the reason? Give the reason. Because third group elements electron configuration is less stable than second group elements, or you can say second group elements electron configuration is more stable than third group. So removal of electron from third group elements is easier than second group. Azuni, am I right? Is the reasoning okay? Okay, good. Fine. So now this I have explained. Now tell me, where is carbon? Where should I put carbon? Carbon is not falling in the category of stable. So carbon will follow the regular trend. Carbon is here. This is carbon. Where is nitrogen? Nitrogen will go up here. This is nitrogen. Regular trend. But nitrogen falls in the category of exactly half-filled stable configuration. You can see. So nitrogen is stable, half-filled. Where this oxygen will go? Will it go here or will it go here? It will go here. Yes. Why? Because it's easy to remove electron from oxygen than nitrogen. And then your fluorine, normal trend. This is fluorine. And then on the top, what is there? Neon. highest. Is this clear, children? So this is how the line will go. Can you see these exceptional drops? These exceptional drops are due to less stable configuration as compared to the previous element. So you can see exceptional drop here and you can see exceptional drop here. So understand this graph. And the graph is here also. You can see the graph. It's there in the notes. I think they have made it for the first period, second period. I made for the third period. They have made for the second period. Oh, this is second period, this is third period, this is fourth period. So second period, lithium, you have the periodic table next to you. Lithium, lowest. Then what is this element, children? This one, this one. Beryllium. What is this one? Boron. Can you see beryllium is more than boron? Beryllium is more than boron. There is a drop here. This drop. This indicates that beryllium has extra stable 2s2 configuration, whereas boron has 2s2 2p1, which is less stable. Which element is this? Carbon. I think I also did the same family. Which element is this? Same period. I did the same period. But somehow I started with sodium and then I started moving with the other elements. Which element is this? Nitrogen. Which element is this? Oxygen. Which element is this? Fluorine. This is new. Can you see in every period, the highest ionization energy is of the noble gases? Symbol of fluorine is F, Afan, not Fl. Fl is some other element. Only F, fluorine. Okay. Can you answer this question? If I compare the ionization energy of phosphorus with sulfur, which one has higher ionization energy? Okay, my question is again, if I'm comparing P with S, look at the periodic table, and only Afan is right. P is more than sulfur. P is NS2, NP3, extra stable. Here is P, children. This is sodium family. Here is P. And here is S. NS2, NP3, P. S is NS2, NP4. In fact, 3. Period number 3. 3s2, 3p3, 3s2, 3p4. So which one is more stable? This one? More stable. So why you are answering sulfur? Aditi, Ritika. What about rest of you? Not understanding anything? Now I want answer from all of you if you have understood this. Which one has higher ionization energy, magnesium or aluminum? Are you looking at the electron configuration? Afan corrected himself. Ritika also corrected herself. Ritika, I think yes. Ritika, good. So Sanjana is wrong, Azuni is wrong, Ashwin is wrong. Lisa, you're right. Sanvi, no answers. Are you listening, Sanvi? You are there? Sanvi. So what is the answer? Sanvi, what is the answer? Okay, children, so magnesium is more than aluminum. Ashwin, is it clear? What is the configuration of magnesium? It is, I think it's period number 3. It is 3s2. In front, there is neon, noble gas configuration. Aluminum is neon, 3s2, 3p1. No, Azuni is period number 3. Period number 4 is for calcium. Period number 3. Okay, answer my question. One more question. Who will have higher ionization energy? Okay, I'm taking you on the periodic table here. I'm circling the elements. Selenium or arsenic. Who will have? Okay, Ritika is answering. Afan, Aditi, very good. Very good. Arsenic is the right answer. Okay, which element will have higher ionization energy? Xenon or iodine? Perfect answer. Which element has higher ionization energy? Argon or xenon? Yes, argon. Down the group, only one factor, size. Very good. Which element has higher ionization energy? Calcium or potassium? Calcium. Which element has higher ionization energy? Antimony or tellurium or iodine or xenon? Put it in the order. So the highest is xenon, then iodine, then Sanjana, then antimony, and then tellurium. Extra stable, Sanjana, extra stable, right? You're understanding? So these kind of questions will be there in multiple choice. And if it is there in the free response, they will ask reason, explain. Because of the smaller size. And Zara is saying why this iodine is more. So first we have to see the size factor. What is happening to the size? Size is decreasing. Then the order should be that xenon, which is smallest, is highest. This is size order. This is size order. But then we know that this is exceptionally stable configuration. So you have to change these places, right? Antimony is NH2NP3. Yes, Ritika is answering your question, Anzara. And this is NH2NP4. Which one is stable? Aditi, did I answer your question also? Are you clear with your question? So you have to just compare stable configuration with the adjacent element. Don't say that this is the most stable, so it's going to be higher than iodine also. No, just with the adjacent, this one. So what we are going to do, I'm going to show you here. I will compare nitrogen family with oxygen family. Exceptional is here only with this oxygen family. I'm not going to compare nitrogen family with halogens. Okay, and I will compare second family with third family with nobody else. I'm not going to compare it with the fourth family or with the first family. So the stable electron configuration can show you an exceptional drop. If this is beryllium, then boron will be down. Then after that is going up. If this is nitrogen, oxygen is down. Then after that, regular. So this exceptional drop you can see here, and this exceptional drop you can see here. This exceptional high you can see here, but that's not, uh, that's the straight line. It's not a drop. Is it clear? So this is graphical representation. So please understand these graphs. You can see all noble gases on the top, all of them with the highest ionization energy. Then after that, we have first, second, third successive ionization energies. So let's try to understand them. Okay. If I give you sodium metal, its electron configuration is neon. Yes, please give me the electron configuration very fast. Take out your periodic tables because we are doing periodic trends. We need periodic table. Neon, 3s1. You remove one electron, you get Na plus one electron. This ionization energy is called as first ionization energy. You are removing first electron. What is the charge on sodium? 0. Now you remove second electron. Second electron you are removing from neon configuration. This is second ionization energy, and it will become Na2 plus one electron is out. Then you remove third electron. It will become Na3 plus. This is IE3. But Na2 plus is helium 2s2 and what is Na3 plus? Is helium 2s2 2p4. Then keep removing. You can remove another. So we have IE1, IE2, IE3, IE4, and so on. You can remove all 11. You can go up to IE11. There are 11 electrons in sodium. 11. Now the question is, what happens to these ionization energy? Are they increasing or they are decreasing? So just focus on this. This can be a question in which explanation, they may ask you the explanation. Which one is higher, IE1 or IE2? Which one is higher and why? Yes, IE2 is higher. IE1 will be lesser. It's always like that. So order will be IE1 lesser than IE2 lesser than IE3 and so on. So Aditi is giving me one reason. That is also accurate, Aditi. But this is the regular order. If there is no noble gas configuration, still this is the order. Why? If I give you an element A, remove first electron, it will become A plus. Remove second electron, it will become A2 plus. Remove third electron, it will become A3 plus. It will become harder to remove electron. Why? Because the element has positive charge. This one has 0 charge. There are more protons, so they will become slightly smaller. Nuclear charge is effective nuclear charge, not the nuclear charge. Effective nuclear charge is increasing. Nuclear charge will be the same because element is not changing. Effective nuclear charge is increasing. So it's holding the electron more tightly. Is it okay? Okay, I'm going to show you sodium here in the table. Children, here on this successive ionization energy, there are two topics. One is PES, photoelectron spectrum. They are also based on this. So here you can see, I'm going to erase it. Sodium is here. I'm highlighting it. Can you see first, second, third? When I'm going from first ionization energy, is it visible, children? This one, first, to second. Second, can you see the number? Let me make it more clear. Can you see the number? Second, this one. It's a big jump of thousands. But after that, it's a regular jump. This is the biggest jump in the complete series. Do you agree with that? Don't worry about later. This is the first big jump. Can I say first big jump of thousands and thousands? This big jump indicates that sodium has only one valence electron. You know, when you are removing sodium, electron from sodium, what's the electron configuration of sodium plus? Neon. And that's what Aditi was talking about. And now this is very hard to remove electron from noble gas configuration. Shell is closed. It's a noble gas. They have the highest ionization energy, big jump, IE1 to IE2. There is a big jump. So it means only one valence electron. So I'm giving you one question here. Ready? There is an element, eyes on the periodic table. There is an element in period number 2. Element, I'm marking it as A, and is undergoing successive ionization like this. There is a big jump from at IE3. There is a big jump at IE3. What is the element? So from the big jump, can you find out what is the how many valence electrons are there? No. Third electron is not valence. Aditi, big jump. IE3 is big jump. It's difficult to remove third electron. So I think Afan has identified the element. So what is the element? With two valence electron. Yes, and Afan was the first one to answer. Good, Afan. Perfect. It means he's doing practice. He's spending time with chemistry. You have to spend time with chemistry. That's it. Okay. Another question. Ready? So I'm going to hide these elements. And if I say this is period number 2, elements of period number 2, can you tell me which element is this? Which element is this? The fourth ionization energy is a big jump from 2000 to 11,000. So which element is this? Yes, it is boron. And which element is this? This one? Yeah, it is carbon. So number of electrons before big jump, if they are saying fifth ionization energy is very high, exceptionally high, then it means it has 4 valence electrons. If they say sixth ionization energy is very high, sixth is very high, exceptionally high, then valence electrons are 5. Then it's a nitrogen family. If they say seventh ionization is very high, then it's oxygen family. If they say the eighth ionization is very high, then it means it's your halogens. And if they say first ionization energy is exceptionally high, noble gases, first ionization, because noble gases are already with inert configuration. So we are good with this. This is your PES. Understand these diagrams because they will be question based on this. You know the electron configuration of nitrogen? We all know that, right? Is 1s2, 2s2, 2p3. This is shell number 1. This is shell number 2. If I make that atomic picture, this is the nucleus. This is shell number 1. And this is shell number 2. So which shell needs highest amount of energy? 1 or 2? I'm talking about shells, not S and P. Shell number 1. Here is shell number 1. See the amount of energy. Here energy is this. You have to check the graph, the coordinates. This is highest energy. So shell number 1 will always be closer to this particular level, highest energy. This is 1s2, children. And the shell number 2, 2s and 2p, they are shell number 2 together. So they will be closely placed. 2s is more higher than 2p. Are you understanding this picture? Is it clear? Can you answer this question? And here is the number of electrons, So 1, 2, height of the peak. So that's why it is 1s2. This is 2s2. This is 2p3. I'm making a picture here. Answer this question. Here is the number of electrons. Here is the energy. And it's like this. Okay. The graph is going like this. You have to identify the element. What is the element? This is shell number 1. Shell number 1 is always. Okay, Afan is already answering it. Very good, Afan. This is 1s2. This is 2s2. 2p6. It means, children, Afan is already answering the question. That's what is needed in the review class. You should be aware of the topic. You should revision, do the review yourself, and then be smart in the class. I cannot teach you everything in the review class. So please open the notes, do some quizzes. And this is 3s1. Perfect, Afan. Okay, now can we do this question? Which element? Which element? Yes, it is 1s2, helium. Only one signal. These are PES diagram, photoelectron spectroscopy. When you introduce your element in PES in this instrument, you get these kind of graphs. And this is the number of electrons, 2. And there is only one signal, means 1s2. That's it. Okay. Can we do next? Which element is this? Yeah, it is P. Perfect. Perfect, everyone. Good. Sanvi, you have understood? You are not answering anything. Sanvi? Okay. Now, this is the diagram of P. You said this is a diagram of P. Can you make the diagram? Then start answering, Sanvi. Answers, they make me comfortable. If somebody is not answering, then I take it that maybe they are not listening. So please start answering those who are not answering. Okay. So this is P. Can you make, please understand this question. Can you make the photoelectron spectrum of sulfur on the top of this? On the top of this. So how many protons are there inside P? 15. I'm explaining you this one. So please listen to this very carefully. How many on sulfur? This is a very popular question. This is real AP exam paper 2018. Sulfur is plus 16. So where the, you know that it is also 1s2, 2s2, 2p6, 3s2, 3p4. This p is also 1s2, 2s2, 2p6, 3s2, 3p3. Now let's compare 1s2 of this and 1s2 of this. Which 1s2 will be more stable? Which 1s2 has more stronger attraction? No, Aditi. Understand this. The graph will shift. Aditi, the graph will shift. You cannot say that, okay, just increase the height. No, no, no. It will shift. The 1s2 of sulfur will be higher in energy because nuclear charge is more. And Zara, you are getting it? This red is for sulfur. And what about this 2s2? That will also be higher. 2p2, 2p6, that will be higher because nuclear charge is more. Can you see it's shifting to the higher energy level? This is 2s2. This is 2p6. Where this 3s2, it will be higher. But where this 3p4 will be? So what happens that P is more stable, 3p3 is more stable than 3p4. So it will be on the right side here, less energy, right? So generally what they do, they make this very close to here, somewhere here, like this. Can you see? This is 3s2, this is 3p4 of sulfur. So please understand when you are making this PES diagram, think about the nuclear charges, right? Ready for the questions, Anvi? This is a real AP exam paper, 2018, official paper. These papers are there on the website already. Element peak X. What is the element here? Is chlorine. So what is this peak X? Which orbital? Let's identify all orbitals. One what? Aditi? One S2. This one? 2s2. This one? 2p6. This one? 3s2. This one? 3p. 3p5. Okay, Aditi, I think maybe you're writing faster than me. Is it okay? You have understood this? Yes, period number 3, chlorine. Yes, Azuni, good. Can we do the first part? So we have identified all the orbitals, right? Identify the orbital, explain the difference. You can explain the difference. This is closest to the nucleus in terms of Coulombic forces of attraction. The one which is closest to the nucleus has the strongest attraction with the nuclear charge. So they are the hardest one to get removed. So that's why their energy needed is called as binding energy, the energy with which it is bound to the nucleus. Energy needed is very high. So you can explain this the way I'm using the language. 1s2 is closest to the nucleus, is strongly attracted by the nucleus. Remember, the force of attraction is K times Q1, Q2. This is Coulomb's law, R squared. This R, if atom is big, if atom is small, like this is your 1s2, R is less, R is less. Force of attraction is more. This is 2s, R is more. This is 2p. 2p just very close to 2s. But still R is more. This is 3s, shell is changing, 3s. R is more. 3p very closely placed to 3s, like this. But still R is more, like this, right? So please make a good reasoning for this answer. You can use the equation, Coulomb's law, or you can simply explain in terms of that 1s is closest to the nucleus. So it has the strongest attraction with the nuclear charge. So hardest to remove. And 3p is farthest from the nucleus. So its attraction is less. So it needs less energy to remove the electron. Ready for this? So they are saying on the same spectrum, you know, this is what? Y is what? 3p5. Now they are asking you on the same spectrum, make for sulfur. So first, you look at the periodic table and answer my question. Sulfur and chlorine, is there any problem with the stability of configuration? Is any one of them with extra stable configuration? No. Very good, Afan. And you know that plus, sulfur is plus 16, chlorine is plus 17. Now this is going to decide in which direction all the signals will move for the sulfur, to the left or to the right. This is low energy and this is high energy. The coordinates are slightly different here. Is going to move to the left. Left is high energy, Afan. So sulfur electrons, they need high energy than chlorine or less energy than chlorine. First, you decide that. Yes, Sanvi, in which direction it will move? Very good, Sanvi. It will move to the right. Yes, Afan, understood? Ashwin, is Arya in the class? Lisa? Okay, so make the graph. They are asking you to make it. You have to draw the peaks. So how the peaks will appear? Like this. This is 1s2 of sulfur. This is 2s2 of sulfur. This is 2p6 of sulfur. This is 3s2 of sulfur. And this is 3p4 of sulfur. 3p4. And you will get full marks. Is it difficult? Can you see the binding energy of chlorine is 273 and that of sulfur is 239. Which orbital they are talking about with this binding energy? Which orbital? Are they talking about 1s2 or are they talking about the outermost? See the range? 1s2. So if this is 273, this one, can I say this is 239? It's lesser. So they are giving you hint. I told you that papers will be easy. In the language, they put the hints. So those who have read the book or the notes, my notes are more than enough. They are like book only. Do the quizzes, read the chapter, whatever time you have now. You can answer the questions very nicely because language is important. They are writing everything. Already hint is given. And with this hint, you can make the graph. Okay, the last topic of this periodicity is electron affinity. Electron affinity. So what is electron affinity, children? Affinity means likeness. Electron means electron. So atom, isolated, see the definition. Definition, everything is given. Right now, you're not using definition. We have to take an isolated gaseous atom because in AP, they don't test you for definitions. But definitions are very, very important to understand the concept. So go through the definition. So here what you are doing, you are adding an electron in the atom. So this is the atom. And when electron is approaching to this atom, what is happening? New attractive forces are made, correct? Why this electron wants to get added? Because this nuclear charge is asking it to come inside, right? There's a positive negative attraction. So new attractions are made. So what is it? Exo, endo. Electron affinity is exothermic or endothermic? Electron is making attractions with the nucleus. It is exothermic. This is a question in the examination. Heat is released. Which one is bigger in size? A or A minus? Ionization energy is endo. Yes, Sanvi. Electron affinity you can write as EA. EA. A minus is bigger. Give the reason, Afan. A minus is bigger, children. Afan is going to give us a reason, which I'm going to use for the second question. Yes, Afan. What's the reason? Anyone knows the reason? A minus is bigger because of? Mhm. Because of what? Azuni, yes. Try to uh, modify it. You're very close to the reason, Azuni. Aditi, Sanvi, I gave you the reason earlier also in that extra class when I was discussing about the size of the anions. It's written in my notes also. Read it, children. More inter-electron repulsion. Use the word inter-electron repulsion. It will help you in answering many questions. Like this one has more electrons. So electrons will repel. Electrons, they repel. When they repel, they try to move away. When they try to move away, size increases. That's why size increasing. Is it okay? Okay, based on this. So please write on this word inter-electron repulsion. It's the part of many explanation. This is first electron affinity. Can I say EA1 first? Now I'm talking about second electron affinity. A minus, this gaining another electron, giving you A2 minus. Only first electron affinity is exothermic. Only first when you are adding electron in a neutral atom. Successive electron affinities, EA2, EA3, they all are endo. Even EA3 is endo. Explain. Heat is needed. This can be a question. only first electron affinity, Ashwin, you're listening? Only first is exo because you are adding electron in a neutral atom, and that neutral atom doesn't have any inter-electron repulsion initially. But after that, you are adding electron into an ion which has inter-electron repulsion, A minus. So now when you want to add electron into this A minus, inter-electron repulsion will dominate. Attraction will not dominate. The repulsion will dominate. And you have to force electron to go inside it. So we need energy to force electron to go inside in an ion which is already with the negative charge. So adding second electron in an anion is always endothermic. Reason? Because inter-electron repulsion is too high, and electron has to overcome this repulsion to get added in the atom, in the ion. Is it okay? You can see the values here. Oxygen. See here. You know, oxygen gains first electron. It's happy to gain first electron. Very happy. And it's exothermic process. Energy is written here. Minus 141. Minus means exo, right? So I'm just writing here 141 kilojoules per mole. But now if I take oxygen minus and will try to add another electron in this, then it becomes O2 minus. And here you can see the energy is needed, 780. But still this is formed. You know, oxygen is always like this. It's never like this. There are other factors also, which I'm not including here because you will get confused. It is formed because of with negative charge, too much of negative charge. It has very high lattice enthalpy, very high hydration enthalpy. So, you know, you see exchange of energy, like we are exchanging money. I'm taking money, giving classes. Your parents are working in the office, getting money. So this is how the money is flowing, right? Then I'm also spending money in some other direction. So same is here. If oxygen needs 780 kilojoules of energy to add second electron, the ion so formed has a very strong negative charge. If Na plus comes closer to it, it will make very strong ionic attraction, very strong lattice. So very large amount of energy is released. So that's how they're compensating each other. Just think energy coin here. Okay. So we are good with this. Okay, there is P. I'm adding P minus. I'm adding second electron to give P2 minus. Is this process endo-exo? This process is endo-exo. It's endo. Very good. If I give you P2 minus, if I add one electron here, is this process endo-exo? This one. This one is endo-exo. Same, endo, inter-electron repulsion. There is a negative charge. Now, if let's say this is EA2 for P and this is EA3, which one is more endothermic? In which case more energy is needed, EA2 or EA3? Yes, EA3. Give one reason. I want you to use that word which I was telling you, memorize this word. Can you use that word? More inter-electron repulsion. Yes, Aditi, either you write more electron repulsion within the ion or more inter-electron repulsion. Very good. Perfect. Now Again, electron affinity depends on two factors. One factor, size. Second factor, the same factor as ionization energy, stability of electron configuration. Stability of electron configuration. So you can see graph with some exceptional behaviors. So I'm going to discuss that. So size. Size across the period, what happens to size? Size decreases. Okay, which atom can gain electron easily? The one which is bigger or the one which is smaller? Which atom can gain electron easily? Bigger one or smaller one? Children, use your Coulombic forces of attraction law. F equals to, this is written in on every page in my notes. In which case the nuclear charge is closer. Here it is closer. Distance is big here. R is more. So always think about it when you are talking about attraction and repulsion. So don't try to answer randomly. Use this law. Okay, so in this case, it's difficult to gain electron. Not easy, right? So which element has higher electron affinity? The smaller one. Here, more attraction, easy. So electron affinity across the period increases or decreases? I'm talking about exothermic across the period. Adding first electron. It increases, yes. And what happens to the size down the group? Size down the group. Increases, yes. So what happens to electron affinity, Afan, Azuni? Yes. Yes, perfect. Good. So, but now anomalous electron configuration. In case of stable electron configuration, the electron affinity will increase or decrease. Stable electron configuration like beryllium. Beryllium is helium 2s2. Do you think beryllium wants to gain electron? Do you think so? No, it doesn't want to gain electron. It's stable configuration. Electron affinity will be nearly zero. You're getting it, children? Now I'm going to show you here in this graph. But I have to discuss one more exceptional trend. And that exceptional trend is this one. This one. After that is regular. Okay. So before we start discussing more about electron affinity, let's go to the periodic table. Here. Can bring it down. So we are going to work with two factors, right? One factor is size. Other factor is your stable configuration. Stable configuration, nearly zero electron affinity. If I say magnesium and sodium, which one is going to have more negative electron affinity? Sodium or magnesium? Mhm. Which one has stable configuration? Which one has stable configuration? Yes. So its electron affinity of the magnesium is nearly 0, right? And sodium electron affinity will be more negative than magnesium. You can see in the graph. I'll show you. Now, based on this electron size and everything, if I ask you to compare fluorine with chlorine, down the group only size is the factor. Which one should have higher electron affinity? But it's the reverse. This is exceptional. Fluorine electron affinity will be, so this can be a question in the exam, is lesser than chlorine. Same with oxygen sulfur. Oxygen electron affinity is lesser than sulfur. Same with nitrogen phosphorus, means this particular period number 2, only here, period number 2 and period number 3. Period number 3 elements have higher electron affinity than period number 2. So, what is the reason? Why is it so? This is exceptional. After that is a regular trend. So, this is one important exception which we have to understand, and we should know the reason also. I told you to memorize one word, inter-electron repulsion. Remember? Okay, if I compare the size of fluorine with chlorine, fluorine has only 2 shells. Chlorine has 3 shells. Big house for electrons, small house for electron. It already have 9 electrons in it, 9. Add one more electron, it becomes too crowded. It wants to gain, it's gaining. Its electron affinity is very high. It's very high as compared to the rest of the periodic table. But it will be lesser than chlorine because the room is so small. Size is too small. Adding one extra electron will cause more inter-electron repulsion as compared to chlorine. Chlorine, it already have 17. What's the atomic number of chlorine? 17, right? It already has 17 electrons. You add one more electron, but still inter-electron repulsion is there, but not so high. It's not so high as compared to fluorine. So what is the reason? I'll answer your question, Aditi. What is the reason? The third period elements, their sizes are slightly bigger than second period elements. So they can accommodate one extra electron with less inter-electron repulsion as compared to second period elements. So third period elements have slightly higher electron affinity than second period elements. No, Aditi. It's just because the second period elements are exceptionally small. They are the smallest atoms. And yes, you can think about it like this. It is 3s, 3p, 3d is introduced but not filled. So you can, but 3d is not interfering here. So there is a change in size from second to third. Second are the smallest. Smallest means already too crowded with electrons. Is it okay? Now ready to discuss questions here? So explain why fluorine has lesser electron affinity than chlorine. Explain. Mhm. Reason? Fluorine is very small. It has plenty of inter-electron repulsion as compared to chlorine. Chlorine is slightly bigger in size it can accommodate extra electron with less inter-electron repulsion than fluorine. You can read all these reasons here in the notes. Okay, what about chlorine and bromine? Why bromine is lesser than chlorine? Give reason. Yes, Afan, when you say fluorine is smaller, talk in terms of inter-electron repulsion. That is the reason I was asking you to repeat, write, speak. That word can answer many questions. Chlorine to bromine. Why bromine has less? Chlorine has more? Yes. Now, the same reasoning, but other way around. Bromine is larger than chlorine, so bromine has less tendency. This time, size, if bromine is bigger, then it has less tendency to gain electron. Now you're not going to talk about inter-electron repulsion. Here the factor is Coulombic forces of attraction. Bromine nucleus is far away from the outermost shell. No, Afan. Atomic radius is the reason. Okay. If bromine is larger, then it should have less inter-electron repulsion. But here question inter-electron repulsion is the minor factor here now. The major factor is size. So size of bromine is much bigger than chlorine. So outermost shell is far away from there's a big difference here in the, so this bromine has less tendency to gain electron as chlorine, right? So down the group, electron affinity decreases with the increase in atomic size. So that reason will work here. Inter-electron repulsion will work only in the comparison of second period with third period. Only here. You know what is this element? Oxygen. What is this element? Sulfur. Can you see? Right? You're understanding this? Look at this carbon and silicon. Same factor. Okay, now why these elements? Like, what is this element? Hydrogen. What is this element? Helium. Why this helium is closer to zero? Because it's a noble gas configuration. And its electron affinity is endothermic. The graph will go down in the positive area. Helium doesn't want to gain electron at all because it's already very stable. This is lithium. What is this? This one? This zero? Look at the periodic table. After lithium, what comes? Beryllium. Can you see beryllium is nearly zero? What's the reason? It is 2s2, stable configuration. Which element is this? Nitrogen, extra stable. Which element is this? Helium. Which element is this? Magnesium. Which element is this? Phosphorus. Is it okay? You're understanding this? This drop. Because this is very stable configuration. Which element is this? It's going down. Which element? 20. Neon. Where? Oh, I was saying neon, but I think by mistake I have written helium. Yes, Aditi, thanks for correcting me. This is neon. Helium is here. You're understanding this, children? So, noble gases, their electron affinity is endothermic because they are very stable configuration. If you want to add electron, you have to force that electron to move inside. So, energy needed. And second period elements, second group. second group elements, and fifth nitrogen family, their electron affinity will be very closer to zero because they are stable configuration. One is fully filled, other one is exactly half filled. Then second period elements, period, compared to third period elements, because of the extra smaller size of second period elements, they suffer slightly more inter-electron repulsion than third period elements. So their electron affinity will be lesser than the third period elements. You can see here every time. Is it okay? So that's the end of the periodic trends. So can I ask questions? This is the last topic, but this last topic I'm going to discuss on the Saturday class. Saturday class is going to be a combined class. So right now I'm just going to do some questions based on periodicity. Ready to answer? So we have done only few trends: ionization energy, atomic size, nuclear charge, and size of the ions, and isoelectronic species. Only few things are there. And electron affinity and successive ionization energy PES diagram. Okay, so start answering. What happens to nuclear charge down the group? Nuclear charge. And make brief notes also. Group, period. Effective nuclear charge. Hmm. This is hydrogen. Here is the electron. Is there anyone in between these two? No. Lithium. Here is the electron. So there is a screening here. These electrons are screening the nucleus. Sodium. These electrons are screening the nucleus. So what is happening to the screening effect down the group? Screening effect is increasing. Very good, Sanjana. So if screening effects is increasing, what happens to nuclear charge? Effective nuclear charge can be written like this, Z effective. What happens to effective nuclear charge? It decreases. Yes, it decreases. Across the period, as you move, let's say second period, how many shells are there in lithium? 2. How many beryllium? 2. Is the screening effect increasing or decreasing? No change. Screening effect, no change. Not valid. Screening effect is valid only if you have some inner shell electrons. So what happens to Z effective? But what is happening to nuclear charge here, children? Then you have to think about the nuclear charge. It has 3 protons, 4 protons, 5 protons. So here Z effective is increasing. Question is why? Because number of protons is the major factor now. Though they are increasing by 1 only, but it's the major factor. Number of protons are going up. So this is one trend which they may ask. Second, size. Size can be explained with the help of Z effective. So group, what is happening to Z effective? What is happening? Decreasing. Attraction is decreasing. What is happening to number of shells? Increasing. So what is happening to size? Decreasing. So with the help of these two factors, you can very easily explain that why the size is decreasing down the group. So please make notes of this. Period. What is happening to Z effective across the period? Increasing. What is happening to the number of shells? No change. No change, right? No change. So this factor is not valid. So do not consider this factor, not valid factor. So what happens to size? Decreases because attraction is increasing. Oh, what did I say? Okay, only Aditi is correcting me. Children, what are you thinking? Z effective is decreasing means attraction is decreasing. Number of shells are increasing means more space around the nucleus. The size is increasing. Did I explain also in the other way? I think I explained right, but I've written this wrong. Are we clear about these size factor? Now let's come to the anions and cations. Ions, size of the ions. Size of ions, that also we did. This is third. First, second, and this is third. So third is the size of ions. So I need some space, so I'm just writing here. So please make good notes of this particular topic. Size of ions. If I give you A and A plus, which one is bigger in size? A or A plus? Which one is bigger in size? A is bigger in size. No, 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 Azuni. Because this one has more effective nuclear charge. Cations are always smaller. You check my notes. Cations are always smaller than neutral atoms. So please memorize it. Why? Because Z effective is more, effective nuclear charge is more. So what reason is Z effective is high for cations. And if I give you A minus and A, which one is bigger in size? I started the class with this question. Which one is bigger in size? A minus. Give the reason now. Inter-electron repulsion, right? You remember? Inter-electron repulsion is more in A minus. They need more space, so they expand to minimize the repulsion. Atom is going to expand to minimize the repulsion. Good. Okay. So that's the size of ions. Now ionization energy and electron affinity. They depend on two factors. What are those two factors? One, size. Second, stability of configuration. Very good. Who is this, Afan? Stability of electron configuration. Aditi, good. Now size will show you a regular trend down the group. So down the group, what is the trend? So let's write down for the group. We are talking about ionization energy, children. So what happens in the group? Is Ritika there in the class? Ritika? Okay. So what happens in the group to ionization energy? Size is the only factor. In the group, you will consider only size factor. Size increases ionization energy. Yes, children? As the size becomes bigger, Yes, it decreases. Memorize it. Because electron goes away from the nucleus, it's easy to remove electron. Effective nuclear charge is decreasing, size is increasing. So you can combine this effective nuclear charge, you can use everywhere in explanation part. But what happens across the period? Across the period, due to size decreases, ionization energy should, must increase. But then stability of configuration is interfering. Stability will show you exceptional drops. Stability of electron configuration. So then you write down second period elements. Oh, sorry, I'm saying period. It's not period, it's group. Second group elements and fifth group elements. Group. They have exceptionally high ionization energy. Second group has higher than third. Fifth group has higher than sixth. Reason, stability of configuration. We discussed that. Is it okay? The last factor we were doing electron affinity. Electron affinity is uh, is also based on two factors. What are the two factors for electron affinity, children? Electron affinity. What are two factors, Azuni? One factor is size. Other factor is stability of electron configuration. Okay, now let's discuss size and stability of electron configuration. So in the group, stability of electron configuration will not interfere because they have nearly same configuration. We did that general configuration, right? So what happens to size? Size increases. What happens to electron affinity? Electron, yes, as size increases, electron affinity mhm, decreases. Ionization energy and electron affinity, they have the same style. Down the group, ionization energy decreases. Down the group, electron affinity decreases. Across the period, ionization energy increases with exceptional jumps. Across the period, electron affinity also increases with exceptional drops, right? So group only size is the factor, but period, stability of electron configuration and size, both of them are going to control it. So size, okay, answer this. What happens to size across the period? It's decreases. So what happens to electron affinity across the period? Increases. But now we have to consider the other factor, stability of configuration. So which particular families have extra stable configuration? Second, fifth, one more, one more. Yes, and eighth. Very good. Who is this? Aditi and Azuni. Very good. Eighth. Their electron affinity will be nearly zero. They will touch at the bottom, nearly zero. You remember the graph? In fact, eighth group elements, their electron affinity is always endothermic. Always. So that's the complete periodic trends. I didn't include the electron configuration. I think we have already mastered it. So when you open my notes, all these things are explained over there, including the electron configuration. And I have made extensive notes You can understand them. Yes, Aditi, you can go. Okay, children, as I said that I will discuss this part in the Saturday class. And in the Saturday class, what else I'm going to do? That class will be lengthier, so come prepared. It will be starting for the PhD students 5, but for the EST student, the class is slightly late 8. And but please come for the class because this is the last weekend where we can have good discussion and we can discuss plenty and plenty of questions. Next weekend, we have one more weekend and you can come there. The classes will be open. But I will be more interested in solving your doubts. You bring your doubts, you bring your questions. So class will be open on your regular days, Tuesday and Thursday and Saturday, but not on Sunday. Sunday I won't take any class because Monday is the exam. So Sunday is not good thing to interact with me. So don't interact with me on Sunday, especially on evening. Morning, yes. If you want to put some questions, I'll answer them. But evening, stay away from me because sometimes children they get nervous. Teacher is saying something and they think that, oh, I don't know this. I don't want you to come under pressure like this. So just by Sunday evening, everything should be over. Whatever you have practiced, close your books, take a nice nap, and go for exam. Okay. So Saturday, Sunday, this weekend, you will be coming for extra class. Saturday, 2017 official paper. Paper is already uploaded on the website also and already given on the WhatsApp. And 20, I think 19 for Monday. And next week, classes are there. You will have 3 classes with me, and the timings will be same. And that you can bring your doubts, your questions. We can discuss more questions. I will also bring more questions, and we'll try to memorize and do plenty of questions. Okay. So today I'm ending the class, and I'll see you then on Saturday. And if you have any questions, you can stay back.